Assalamualaikum. Hi, good afternoon. Introduce myself. My name is Widya Dewi. I'm a math student for semester, Faculty of Science and Technology, State Islamic University, Sunan Gunung Bandung. In this video, I will explain about mappings. The most fundamental concept in modern algebra is that of an operation on a set. Addition and the other operation in the familiar number system are examples, but we shall see that the general concept of operation is much broader than that. Before looking at operation, however, we devote several sections to some basic terminology and fact about mappings, which will be just as important for us as operation. The word function and mapping are synonymous. Therefore, at least some of this material on mapping will be familiar from calculus and elsewhere. Our context for mappings will be more general than that in calculus, however, and one of the reasons we use mapping rather than function is to emphasize this generality. Notice that elementary facts about sets are collected in Appendix A. They will be used without explicit reference and probably should be reviewed at this time. You are also used to real Appendix B, which reviews some element of logic and offers suggestions regarding proofs. Mappings. Mappings are important throughout mathematics in calculus. For instance, we study mappings or functions that assign real numbers to real numbers. The mapping given by fx is x squared. For example, assign to each real number x the real number x squared. The mapping given by fx is sin x. Assign to each real number x the real number sin x. The set R of real numbers plays two roles in this example. First, x element R, and second, fx element R. In general, these roles can be played by sets other than R. Thus, in the definition of mappings, which follows, S and T can denote any sets whatsoever. Definition. A mapping from a set S to the set T is a relationship rule correspondence that assigns to each element of S a uniquely determined element of T. The set is called to the domain of the mapping, and the set T is called the codomain. An alternative definition of mappings preferred by some is given at the end of Appendix A. Mappings will generally be denoted by Greek letters, and to indicate that alpha is a mapping from S to T, we shall write alpha S to T or alpha S to T. If X is an element of S, then alpha X will denote the unique element of T that is assigned to X. The element alpha X is called the image of X under the mapping alpha. Sometimes there will be a formula for alpha X. As in the examples, fx is x squared and fx is sin x, but there certainly need not be the case. Example 1.1. Let S is x, y, z, and t 1, 2, 3. Then alpha defined by alpha x is 2, alpha y is 1, and alpha z is 3. Is a mapping from S to T. Another mapping, beta S to T, is given by beta x is 1, beta y is 3, and beta z is 1. The following diagram does not represent a mapping from S to T for two reasons. First, it assigns two different elements to X, and second, it assigns not element to Y. This is not a mapping. S explained in Appendix B, all is a universal quantivity. Then, the negation of a statement with a universal quantifier is a statement with an existential quantifier. All is universal, whereas there is and there exists are existential. Thus, example 1.1 give two different mapping, alpha and beta from S to T. There are, in fact, 27 different mappings from S to T for S and T. As in example 1.1, the result is that we have three independent choice, 1, 2, or 3, for where to map each of X, Y, and Z. Thus, the total number of choice is 3.3.3 is 3 cubed is 27. The choice for where to map X and the same for each of Y and Z. Example 1.3. If S is any set, we shall use oita to denote the identity mapping from S to S, which is defined by iota X is X for each X element S. If it is necessary to indicate which set S is being considered, iota S can be written instead of iota. It is sometimes convenient to write X to Y or X to Y to indicate that Y is the image of X under a mapping. Example 1.4. The rule S, T to S plus T for each ordered pair of real numbers S and T defines a mapping from the set of ordered pairs of real numbers to the set of real numbers that S, T is ordered means that it is to be distinguished from T, S. The necessary for this distinction can be seen if addition is replaced by subtraction T minus S, not same with S minus T, unless S is T. Mappings of this kind, assigning single elements of a set to pairs of elements from the same set, will be discussed at length in section 3. If alpha is S to T and A is a subset of S, then alpha A will denote the set of elements of T that are image of elements of A under the mapping alpha. In set builder notation described in Appendix A, alpha A is alpha X who X element A. The set alpha A is called the image of A under the mapping A. Example 1.5. With alpha and beta is in example 1.1. Alpha X, Z is 2, 3 and beta of X, Z is 1. Definition: if alpha S to T, then alpha S will be called the image of A of alpha. If alpha S to T and alpha S is T, then alpha is said to be onto. Thus, alpha is onto if for each Y element T, there is at least one X element S such that alpha X is Y. Example 1.6. In terms of diagrams like those in example 1.1, a mapping is on to provide each element of the codomain has at least one arrow pointing to it. Thus, the mapping alpha in example 1.1 is on top. However, the mapping B in example 1.1 is not on top. Its image is 1, 3. which is a proper subset of 1, 2, 3, the codomain of beta. Example 1.7. With fx is x squared and gx is sin x of S mappings from R to R, neither is onto. The image of f is the set of non-negative real numbers. The image of G is the set of real numbers between -1 and 1, inclusive. Definition: A mapping alpha S to T is said to be 1 to 1 if x1 not same with x2 implies alpha x1 is not same with alpha x2. x1, x2 is element of S. That is, if unequal elements in the domain have unequal image in the codomain. Example 1.8. In terms of diagrams, like this in example 1.1, a mapping is 1 to 1, provide no two arrows point to the same element. The mapping alpha in example 1.1 is 1 to 1. However, the mapping beta in example 1.1 is not 1.1 to 1 because x not same with z, but beta x is same with beta z. Example 1.9. The mapping fx is x squared with domain R is not 1 to 1 because fx is x squared. And then x squared is f minus x. Although x doesn't same with minus x when x doesn't know. The mapping fx is since x with domain R is not 1 to 1 because fx is sin x plus 2np is fx plus 2np for each x element of R and each integer n. The contrapositive of x1 doesn't same contrapositive x1 not same implies alpha x1 not same with alpha x2 is alpha x1 is alpha x2 implies x1 is x2. See Appendix B for discussion of contrapositive statements. Since a statement and its contrapositive are equivalent, we see that alpha is S to T is 1 to 1. If alpha x1 is alpha x2 implies x1 is x2, who x1 and x2 is element of S. It is sometimes easier to work with this latter condition than with that given in the definition with alpha is R to R defined by alpha x is x minus 1. For instance, we have that alpha x1 is alpha x2 implies x1 minus 1 is x2 minus 2, which implies x1 is minus 2 or x1 same with x2. Therefore, alpha is 1 to 1. Notice that the identity mapping on any set is both onto and 1 to 1. Notice also that a mapping of a finite set to itself is onto if it is 1 to 1. In contrast, there are mappings of any infinite set to itself that are 1 to 1 but not onto, and also mapping there are onto but not 1 to 1. Here are some examples. Example 1.10. We find mappings alpha and beta from the set of natural numbers 1, 2, 3, and then to itself by alpha n is 2n. and beta n is n plus 1 for 2 if n is odd, and n for 2 if n is even. Then alpha is 1 to 1 but not onto, and b is onto but not 1 to 1. The existence of submatrix is precisely what distinguishes infinite sets from finite sets. In fact, a set S can be defined as infinite if there exists a mapping from S to S that is 1 to 1 but not onto, otherwise S is infinite. We close the section with one remark on notation and other on terminology. The symbol N, Z, Q, R, and C will be reserved to denote the following sets. And the sets of all natural number 1, 2, 3, and then Z, the set of all integer -2, -1, 0, 1, 2, and then Q, the set of all rational numbers, that is, real numbers that can be expressed in the form A per B with A, B, element Z, and B not 0, are the set of all real numbers. C, the set of all complex numbers. That's all. Thanks for your attention. Thanks for watching. Assalamualaikum warahmatullahi wabarakatuh.